Okay, so what we have here is the Jurassic gneiss. Okay, the green color is because it's highly chloratized.
Yeah.
If you look at it close, it's very fragmented.
Yeah.
Okay, I would call this a breccia to microbreccia. Okay,
With
just
just little
beneath it,
feldspar crystals.
just beneath it, you see this red stuff here.
Yeah.
Okay, that's foliated gouge. Foliated gouge. All of this red stuff is derived from the Keishan volcanoes.
Okay.
Okay. Now, when you start here, and there are seams of foliated gouge
Yep.
that cut through
In
it.
with the-
Okay. So what we're going to use here is fault zone architecture terminology. Okay. So what we do here is this is called the fault core. Okay. This piece right into going from here to just about where Brian is standing, a little bit further back, right there, right there. That's the inner damage zone. Okay.
Yeah, yeah.
If you go up and you look at it, it's very broken and fragmented. There's lots of little veins and fractures shooting through it, and so on and so forth. Okay. Now, if we then go back further from here, okay, if we just simply walk down this way, as you look, notice the rocks are light gray. Can you see all the veins
Yeah,
and fragmentation
lots of
going on?
veins. Yeah.
Okay. And that will go all the way to the bend in the road.
Yeah.
Okay. In the ravine.
In the ravine.
At about the bend in the ravine is where we would place the limits of this fault zone.
All right.
Okay. So that's the outer damage zone, inner damage zone, fault core. Okay. Now the way this works is we can literally track the Keishan then right into this, track it all the way up to the fault. Okay. And so here's the trick. We collected 57 samples. Okay. And we collected them from the high ridges coming straight across in this broad swath right into here. Okay. We collected samples from the damage zone, the inner and the outer, and samples from the fault core.
Now, what about
remember,
what about on the far side? Is same? You'll tell us.
So-
Pardon me.
So remember the rare earth element patterns. Remember how tight they were? Okay. So if the rare earth elements are not affected by fluids as they circulate through this fault zone, then they provide us a framework from which we can measure changes in volume associated with the development of the fault core and the damage zones. We can also track changes in elemental mass all the way down to individual elements, right? We can also track changes in bulk mass. So by doing this, we should be able to quantify exactly what's happened. We can write mass balance equations to do all of that. And then Tom should be able to tell us exactly what happened here. Okay, and that's his goal. That's what he's going to do. And he'll finish his thesis by June, and you're welcome to come and hear it. Okay, it should be a really, truly outstanding piece of work. Tom Colby. Tom Colby.
Which?
Tom Colby.
Oh, not here?
No, he's not here. He's at Washington State doing microprobe work this weekend. Okay, you get it? Understand? Okay. And I'm really, really anxious to see what happens here. Okay. So this is a contractional fault. Okay. So then we would predict, based on that basis, that the volumetric strains in that fault gouge should be negative. We should be losing mass. Okay, because we're dissolving and it's a shortening type of thing. If this was a pure extensional fault, I would predict dilational strains. Okay, and if we're right, if we get lots of mass loss here and we get negative volumetric strains, then we've just developed a new technique at looking at these faults, so how to identify the types of changes associated with them.
If you have volcanics.
Well, what this requires is you have to have something like the Keishan, where you've got these rare earth elements that are so tight,
Yeah.
right? And so you've got a really tight constraint on what those things look like, right?
Okay.
So as we track them in here, I want them to not change.
Yeah.
Okay? And if they don't change, then I have a framework from which I can measure all kinds of changes associated.
We're going to tell TC Chamberlain.
So I'm pretty excited about this. Tom is, he's off his rocker waiting to get all this done.
Okay, now, assuming you're right that this is a contraction.
Yeah.
Okay, now where do you go? What's the next step?
Well, the next step is I would like to see, well, all right, so if this,
the assumption.
okay, if this is north-south shortening and this is post 9.45, then to me this absolutely nails that story closed, right? You just put a nail in it. right? And so nobody can deny that now at this point. And so if this is a strong north-south shortening component, much of the structure that people have interpreted in the past as due to extension is not. It's in fact due to this north-south shortening event. And so when we stand here, we're right on the edge of the North American plate as the San Andreas Fault system begins to develop at about 12 million years ago. We're right along the edge of it. This part here is moving that way, and this part is just, and the strains are just starting to get going here. So you're having breaking and cracking, some slip going on. And further to the south, you start to develop the eastern segments of the eastern California shear zone where there's major slip coming. All that slip, as it comes down to here, is transferred into this. Okay? Just like the series of faults on the western San Andreas going into the transverse ranges. Beautiful analogy.
Okay.
And that's the story.
Okay. Assumption, if you're wrong, if it's dilational.
It won't be.
Well,
It won't be.
Gary, bubble.
It won't. I don't even need to think about that.
We're gonna all show up at the thesis then.
If it turns out to be dilational, I'm going to have to think long and hard about it.
Okay. Well, that's a good answer. Okay.
And I have a possible
Okay.
explanation for that.
Now, what about the other side of the fault?
Okay, the other side of the fault I need to work on.
Yeah, that's what I'm
Okay, I really would. In fact, we came out here, and what I wanted to do, the first thing was actually map and see where the chlorite dies off. Okay, and we started doing some work on that. The problem is we got all the way to the top of the hill, and there was still quite a bit of chloride in it. However, we haven't collected the thin sections. If we collected the thin sections, did the point count, my assumption would be, again, dominant chloride here, and chloride is dying off as you go into the
So
structurally
would you
higher
see a
package.
mirror of this
Yep.
over there?
Yep.
That's what I was
Yep.
wondering.
Yep. It's the exact mirror, except that this is going to be much more heterogeneous than this, and so you can't do all of the things I want to do with
Because
this.
of the different rock
Yep.
types. Okay.
Yep.
Oh yeah.
Yep.
Gary, on the timing, is it possible that it could have been normal detachment?
I don't see how it's possible.
I'm talking timing wise. Is that it wouldn't default that this could have been a reactivation of a normal surface?
No. In fact, I agree with you.
Okay, I
In
thought
fact,
you were saying
no.
it was flip flopping completely
No.
again.
No.
It's a sequential
I
thing.
agree with you. This
Okay.
could have been a detachment fault initially that was reactivated.
When the strike slip
Yep.
faulting started.
So in other words, but see the problem is if you want to do that, now just think about what you just said.
Uh-huh.
Okay, if this is a detachment, then the gneiss has to be on top of the caisson.
Oh yeah, no, yeah.
Well, how in the hell did it get there?
Well, if you had two units, I mean, okay, let me diverge to a different place. If this is a surface deposition,
Yeah.
right here,
Yeah.
it's a surface deposition.
Yeah.
That suggests that, and this was all offset 5 million years ago from 3,000 kilometers south, so it's actually moved up. And if this was a surface expression, it really hasn't come up. I mean, so it's a surface. That means all these faults that we're looking at were very near the surface. Would you agree to that?
Well, in fact, I would say that this one may have actually broken the surface.
Okay. Because I mean, I always thought that detachment faults, if these are, detachment faults, I always thought they were deeper because they needed more.
In fact, this one, if we trace it past Little Picacho Peak and on, this fault actually places the gneiss over Bear Canyon conglomerates.
Okay.
So I
So
think
was
it actually
very
broke
near
the surface.
Because I always assumed that there was a lot of uplift
No.
in the translation northward, and so no. Wow.
Is the fault
But
plane
it's-
folded?
This fault plane is not folded. And what's cool over there is when you can actually see it dipping to the south. Here's the gneiss in the Bear Canyon, this beautiful overturned syncline. Again, and if you remember how drag works, right? So it's moving up towards the north. Okay?
But if this broke the surface, this right here must have been fairly deep to have had the confining pressure to create.
Well, no, the foliated gouts tells you again that you're looking at very high crustal levels. Confining pressure here is minimal.
Minimum.
Yeah, So,
So how far was the surface from here?
I mean, we don't really know, but I would estimate here that you're probably looking at this can't be any deeper than maybe, if you push it, I would say 1 kilometer.
Well, okay. Well,
And I think that's
right.
pushing
That's what
it.
I'm saying. It had some confining pressure to create this.
There probably would have been more
not
volcanics
much.
on top of it.
Yeah.
More volcanics just piled up. And then,
Well, I mean, I think it might have looked, if you go down 1 kilometer, it probably looked I mean, this is what it would have looked
Yeah.
like. This would have went up to the surface, and the gneiss would have been sitting there, moving up and over the Keishan. As you go over there, the Bear Canyon conglomerate would have been pushing right up over it.
Why do you say that can be deeper?
Well, because when you look at the development of fault zone rocks, okay, you can break them up into 3 different series, okay, and the 3 different series are related to how much confining pressure is